An object is hanging from your rear view mirror. Your car accelerates this direction, and during the acceleration, the object hanging from your rear view mirror swings backwards, creating an angle of theta between the vertical. If the car's acceleration is 3 meters per second squared, what is the angle? Get started. You don't need any other information from me. And if you're wondering where to start, I gave you a whole set of steps. This is a force problem. It involves acceleration, and clearly the forces have something to do with that. So get started. You have a set of steps. Attempt to use them. But you have a series of things to do. So you've indicated this is the second law problem because our system is accelerating, okay? Second law problem. I'm going to begin by taking the mass of the object, the dice. That's what we're interested in, reducing them down to a single dot to represent their mass. I'm going to start by asking, are there any fundamental forces acting on the dice? Yes, so I will draw an arrow indicating that there is a downward force due to gravity. Straightforward enough. Is there anything in contact with the dice?
Yes.
What? The string. What kind of force does the string apply to the dice? A tension force. So I will draw another arrow in the direction of the string. I think that's pretty close. Pretty close. And I shall call that tension. Excellent. Are there any other forces acting on the dice?
Yes.
What? What's touching the dice? The air moves with the car, luckily. So I don't think that I have to worry about the air so much. We prefer the air to move with the car. Otherwise, you might suffocate. I think this is it. Nothing else acting on the dice. I know you want there to be a force pulling them this way, but they are actually resisting the urge to move, which is why they swing upwards. They want to stay in place. It takes an unbalanced force to get them to move. There has to be something that causes an acceleration to the right. The forces have to be unbalanced. Why would you balance the forces out? That would suggest that they're not accelerating. We want the dice to accelerate. When you are going at a constant speed, the dice just hang there. They don't stay back the whole time you're driving. They're only back when you accelerate. So that would mean starting, stopping, turning left, turning right. That's when they move around. All the other times, the stuff just hangs there. All right. Seems to me like my next job is to decide a coordinate system that would be aligned with the direction of the acceleration, since this is a system that accelerates. So I will draw in a coordinate system that is aligned with the direction of the acceleration. That suggests this way, since it's going to accelerate to the right. I'll make that the positive x direction. Now I think I'll need a vertical one that's got to be perpendicular to the horizontal. There we go. Do I have any off-axis forces? Yes. I do. I think I'll need to break the tension up into two components, one in the x direction and one in the y direction. I'll need to place the angle in the appropriate place over there. I'm thinking that would be here. Do we all understand why? Yeah, really? What's the geometric principle that would say that would be where the angle goes? Do you remember it? No, it would not be. Boy, you guys think you know stuff, but oftentimes I'm surprised. If I have two parallel lines cut by a transverse, the alternate interior angles are congruent. Correct? Let's use the right geometry, guys. You love those A's. Let's make sure we use them. All right, I need to break this up into components, so I'm thinking there'll be a component that is upwards and a component that is to the right. Based on my cursory understanding of trig, albeit slim understanding, this will be t sine theta, and this will be t cosine theta. Luckily, I have all the mathletes here to keep me honest. Any questions about those choices? Well, once I have my components, I don't have to use this anymore. I can get rid of all of that. And I'll just take this, put it right down there. Seems to me I'm ready to employ Newton's laws, which allow me to take net force in the x direction, net force in the y direction. Which one of these will I set equal to 0? Excellent. Part of that string is going to be keeping the dice from falling to the floor, and part of that string is accelerating the dice to the right. I don't have the mass of the dice. I don't think I need them. In the y direction, t cosine theta minus mg equals 0. And then the horizontal direction, t sine theta equals ma. Any questions there? I think I see a pathway to figure out what the angle is. Probably substitution would be what you guys would do. Do you guys see some substitution there? I'm not going to do substitution because that's old. And there are new ways to do math, or at least more efficient ways to do math. Do you remember that you can divide both sides of an equation by the same thing? Well, I'm going to divide both sides of the equation by the same thing. I'm going to divide the left side by t cosine theta and the right side by mg. Because those things are equivalent, I'm dividing both sides of the equations by the same thing. That cancels the t's and cancels the m, and lets me know that tangent theta equals a over g. Not hard. Only two forces. This also tells me that you can make a cheap accelerometer, a device to detect acceleration. All you need is a protractor and a hanging weight. And based on the angle, it can tell you how many G's you experience. 45 degrees would be 1 G. Not terrible. Ready for another one? Try another one. So I have a book with a calculator resting on its cover. When I crack the book open 20 degrees, if there's nearly no friction, what will be the acceleration of the calculator down the cover of the book? So we'll start by saying this is a second law problem. Net force equals ma. I'll take the calculator, reduce it down to a dot. And I don't think I need to ask you guys all the different forces at this point. Did you draw a downward arrow?
Yeah.
Excellent. And what did you label that?
W.
All right. W equals mg. Is there anything in contact with the calculator?
Yes.
What's in contact with the calculator? The book. What kind of force does the book apply to the calculator?
Normal.
Normal forces must be perpendicular to the surface in contact. That is perpendicular to the surface of the book. Would you agree?
Yes.
Pretty close. So there we go. I'll call that a normal force. Anything else acting on the calculator?
No.
Strings, ropes,
No.
friction, we said no. That's it. Two forces act on the calculator. I'm going to need to draw a coordinate system. I'm going to use as a priority a coordinate system that is aligned with the direction of the acceleration. And when I watched that, I'm pretty sure I saw the calculator accelerate down the ramp. So let's align my coordinate system with the ramp. There we go. I'm going to make this the positive x direction. That means my positive y direction, something like that. All right, well, it looks like I have an off-axis force. Do you guys agree? I'm going to need to deal with my off-axis force. So before I do, where does the 20 degrees go? Does it go in column A or column B? It's a lot of quiet in 1A. How about this? If I start closing the book, which one of those two is also going to get smaller? A or B? A. If I start closing the book, A gets smaller because the normal force starts pointing more upwards. Agreed? So I think A must be our 20 degrees. That's not a proof, but that's a reasonable explanation. Agreed? If you want a proof, go ahead. There's a lot of triangles there. You can probably figure it out. If you don't care about proving it, I will just tell you that the angle of the incline will also be the angle between the weight and a line through the normal force. Look, if you're barely holding on with what we're doing today, I just gave you a piece of very important information that I would never put on a cheat sheet, but you might want to memorize it. The angle of an incline will be the angle between the weight and a line through the normal force. Alrighty. That being said, that makes this our 20 degrees. I'm going to break this up into components. I'm going to draw a component in this direction, and then turn and draw a component in this direction. But I've been doing this for a very long time. I'm saying this because one of you, and I don't know who it is yet, but I'm looking forward to the person who will make their components look like this on the next test. I promise to hang this up in class. I promise to put it on the bulletin board in front of all the NHS stuff that they never hung up on my bulletin board and make sure we all see it prominently in class. Do you understand why this can't possibly be true? If you don't understand, I will tell you. But remember, the red arrow is the actual force. The green arrows are the components. And components must be perpendicular to each other and aligned with the axis. Are those two forces both aligned with the axis?
No.
No, they are not. So we'll do that right. And don't be the person whose test I put up there, because I'll probably get nasty grams for your mommy or daddy. There we go. Now, when I look at that, I see that this must be mg sine 20 degrees, and this must be mg cosine 20 degrees. How are you guys with that? You guys see that too? Opposite gets the sine and adjacent gets the cosine. So I think now that I have identified my components, I can get rid of the force that I put there originally. And let's see, just move my, there we go. Mg sine theta. All right. Well, I think we're coming into the home stretch. Net force in the x direction equals net force in the y direction equals, which one of those gets ma? Well, I already put the 0 down. Oh well. There we go. I see just mg sine theta equals ma. I also see that normal minus mg cosine theta equals 0. But it seems very clear I could figure out the acceleration with what I have there. Do you notice the m's seem to cancel out? It's a product of inertial mass and gravitational mass being the same, and the acceleration is just g sine theta, 3.4 meters per second squared. Not terrible, just two forces, right? Not terrible? We'll see. I'm glad these weren't your quizzes today. But tomorrow, of course, these are all in the homework. Anybody try the homework yet? I haven't made up anything that's in homework. It's all in the homework. I would try some. I got another one. I was hoping to get 3 of these in today. I got time for one more. Oh, that's terribly ugly. Terrible. Let's do a better job, Mr. Sheldon. If this is an equilibrium, how many forces are acting on the weight? Can you name one? Okay, tension. We'll start there, I guess. I'm pretty sure tension is upwards. Any other force acting on the weight? Gravity, that's a good one. I'll point out that today, none of the examples had more than 2 forces in them. It's a first law problem or a second law problem? So net force equals 0. That suggests the tension equals the weight. Not terrible, right? What's providing the tension, though? The spring is providing a tension. If it is a Hooke's law spring, we would have to test it to see if it's a Hooke's law spring. But if it is a Hooke's law spring, then the force of the spring is proportional to the displacement. I just said it using math, right? That's what proportional to means. Linear relationship, direct proportion. Double delta x, and I double the force from the spring. However, physics requires that we do more than this. Physics requires that I tell you that displacement is a vector, and force is a vector. And if the spring is displaced downwards, then the force from the spring must be upwards. That's Hooke's law, because it has to handle both direction and magnitude. Now, like I said, this spring was stretched 9.5 centimeters, which is 0.095 meters. Newtons is in meters, so if you're given a value in centimeters, you'll probably have to convert. And I said that the mass that I hung was 200 grams, which I'm sure all of you know is 0.2 kilograms. Well, if I wanted the linear spring constant, sometimes called the Hooke's law constant, I think I have a method to do so. You see, I know the tension in the spring had to be equal to the mass that was applied, 0.2 kilograms, and the acceleration of gravity, 10 meters per second squared, giving me a tension in the spring of 2 newtons. It's a spring, so that had to result in the spring stretching. How much did the spring stretch? Well, the spring stretched downwards 0.095 meters. You see why I made the 0.095 negative? Displacement has direction, so I have to make sure I'm being consistent. Now that negative times a negative is going to give me a positive because all spring constants are scalars and don't have direction. So this has to be a number that has no positive or negative. And I'll find that K is equal to, 21?
Yes.
Units, newtons per meter. You see, the spring constant tells you how strong the spring is. A stronger spring won't stretch as much when a force is applied. So a weaker spring will stretch a lot. This is a pretty weak spring. I bet sorry to bore you, I bet the springs on your cars are a much bigger number. I think when you put all of your weight in there, maybe several hundred newtons, does your car springs go down very much? I mean, does your car sink a lot when you go to sit in it? I'd argue it probably doesn't, so I'd say it probably has really, really high spring constants. But I'd say that I wouldn't want you guys to sit on the end of this spring. I don't think it would. I think you would bend the spring. I think you would reach the physical limit of the spring. 3 examples. None of them had more than 2 forces in them. It's your homework stuff. We got more to go. And I have 2 minutes, so I'm going to use them. But are there any questions about these 3 examples that we've talked about? All right, then